All right. Welcome back to Operating Systems in Crates.io, which is what this class is turning into. How's everyone doing? Okay, so why'd I turn on the stream for this? I don't know how far we're going to get today. That says 82 at the bottom. That's unlikely to finish. So, definitely no homework this week, but you have to have a double fault handler on your operating system somehow. And so, maybe that's the lab this week. Or maybe you're just responsible for getting that done, and we watch Ghost in the Shell 1995 on Wednesday. See, I was thinking it would be easier for you to get the double fault handler done if we watched Ghost in the Shell, right? Apparently it's only PG-13, which I wouldn't have guessed. So, I am not your parents. Do not ask me about any content in that film. Okay. Okay. Also, I just downloaded it from one of my friends. So, I have it now, and it seems to work. You should have testing done is like an obscure way to say this. Your testing framework should be done. You should be adding tests to it over time. A lot of the content today is going to be adding new tests and then solving the problems that the tests detect and then adding test cases that cause problems. The first handler is assigned, and that's the wrong one. That's the breakpoint handler. That's this thing right here. So this is due Friday. Which, it's getting kind of close to break, too. That's fine. I had a good time writing handlers. Jimmy, you missed it. I referred to this class as Operating Systems in Crates.io, which is, okay. I thought you'd like that. No, okay, never mind, fine. I'll save all my jokes for other people. Okay, CPU exception. Okay, I already said this last time. Okay, I had to name the slides today something, and I went for a shorter name, so I called it double. And then I realized that some people might think that's referring to the double floating point type, so this is my disclaimer. That's all. It's nothing too exciting. Okay, I am going to reload your brains. We are going to engage in a context switch back to where we were at the end of last class, because this just feels like one contiguous block to me. Okay, CPU exceptions occur when things go wrong. What is the thing that goes wrong? Divide by 0, unauthorized memory read. Other stuff can happen. You can try and process an instruction that doesn't exist on your architecture, okay? So you have to deal with this by setting up an interrupt descriptor table. What is the interrupt descriptor table? The operating system, when it comes online, populates a series of memory addresses and tells the CPU about those memory addresses. When the CPU hits a problem, it looks at that table and decides what address to load. The address to load is programmed by the operating system. Okay, at those memory addresses that are loaded, there are certain handler functions. The handler function is supposed to deal with whatever problem is encountered. This is a complete handshake between hardware and software. Software causes a problem, hardware flags the problem, asks the software to solve the problem, the software solves the problem that the hardware alerts. So you are back and forth all the time. Extremely, for that reason, like much more an operating systems topic than almost anything else can be, because you're going back and forth between OS. Okay. Last week we dealt with the breakpoint exception, which is boring in the sense that it's mostly used by debuggers, and we don't use debuggers, we just write the code right the first time. Isn't that right? Can I get a hell yeah? Okay, not a single one. Okay, all right. Can I get a maybe?
Sure.
Okay, I like the maybes. That's pretty good. I want you to know, this week, I was writing my double fault handler, and I didn't follow the blog. I just wrote a bunch of code, and it did work on the first time. Okay? So, I was surprised too. But, not that surprised. Sometimes things just work in Rust. It's kind of weird. Nothing ever just works in C. So, we set up an interrupt descriptor table. That was our part of the collaboration between the hardware and the software. I do think we got the good end of the bargain with this. I think probably the hardware people had to work a lot harder than we did to get this to work. But fundamentally, the hardware isn't going to work at all if it can't recover from problems. So, good deal. Okay, anyways, this week we're going to work on double faults. Double faults are the I'm going to say they're the fault of last resort, because if something is worse than a double fault, it's kind of not a fault anymore. It's just a restart. Okay. This is the description of a double fault. I will just tell you the colloquial definition, which is not correct, but is close enough. If you encounter a fault while dealing with another fault, that is a double fault. Is that true? Not always, right? So it's like quasi-legal to like hit a page fault after a divide by zero, because those things aren't really related to each other. But in general, we think of the double fault as an escalation beyond a typical fault. So we're going to handle it. Okay. The functional definition, not perhaps the semantic definition, is that a double fault is invoked. Now, I poisoned my brain because this says invoked. A double fault is the description of the state that occurs when the CPU hits an exception, looks up the exception handler in the interrupt description table, and there's nothing there, or there's something erroneous there, or whatever. But so the second fault is not just an exception is raised while dealing with an exception. It's that the exception is I do not have an exception handler. So a page fault is triggered without a page fault handler registered. So I try to look up a memory address. That memory address doesn't exist. That's my first problem. Okay. The hardware says, okay, the memory address doesn't exist. No problem. I know how to deal with this. I will inform the operating system, and I will inform it in the following way. I will look at a table that the operating system has populated. I will take an entry from that table, and I will load the function at that memory address. And so the hardware goes to do this, and it sees that there's nothing in the interrupt descriptor table. So it instead attempts to load a different address, which is the address of the double fault handler. Okay. This is kind of the same thing as a generalized exception in Python. So I think you all know I love writing Python. Why do I do this? So, how do you do try? Does this look like Python to everyone?
Yeah.
Okay, so does not check if this is a divide by zero error or anything else. I think there is like try catch, right? Try. Does this look like Python?
I think you just have to do accept here. Does it?
It's accept?
Let me check. I don't remember do error handling in Python. I don't like Python to handle errors.
Yeah, you write Rust to do that. Zero div. And then we'll maybe hit an accept. Print
Yeah, I know. It's just accept. Yeah.
Look at that! Look at that! We figured out. We learned Python today. Okay, so we don't really call this a single fault. So this is the divide by zero fault, right? This is the double fault. Because if this weren't a divide by zero error, we don't have a specific exception handler written for it, so we would go there. Okay. Okay. All right. How does the double fault handler work? So it's a normal exception, but because of the circumstances under which it can occur, it like doesn't feel normal. Like you have to deal with many more corner cases. Think about this not necessarily from the term of OS design right now, actually, but think of this from the perspective of course design. Why do we teach the double fault handler second? We teach the absolute easiest fault handler first, so that you have an example of a fault handler. Then we teach the most general fault handler second, so you know how to deal with all the other problems you're likely to experience writing other fault handlers. That's fundamentally the problem we're solving today, right? That's why we're doing double faults today. The double fault is like independently interesting, but that's really what's going on. Okay, if you fail to provide a double fault handler, you can get a fatal triple fault. What does fatal mean? It means the system reboots. It's not like the hardware melts or something, right? So fatal is kind of a strong claim. It's software fatal, but hardware no problem. Triple faults can't be caught by definition. It is not a triple fault if you can catch it. I wonder if there's anything we can't catch in Python. Like, maybe if I, like, my sound is on? Oh, I was watching anime. Why'd I say that? Okay. Typing is super hard. Okay. So try os.system kill 91520. Okay, right. So like I'm pretty sure Python's not going to be able to recover from this.
I don't know if it's because of the try except. Is this going to cause an exception?
Yeah, so I think this is going to be an unrecoverable. I think we're going to triple fault Python right here. Take that, Python. We got him. We got him. And so this is logically equivalent to how my operating system would have a hard time dealing with me throwing it into a volcano, right? It would be very difficult for the operating system to recover from that. So that's an example of a triple fault. Volcanoes, many other natural disasters, force majeure events, things of that nature. I just want to point out that I first time YOLO coded a way to get around the Python exception handler. I just want to do that in your job interviews, and everyone will be like, "No, we're not going to hire you." That's what they'll say. Okay. Did you all know I got a job here? I live coded Python in my job interview, and they were like, "Why is this a mix of functional and object-oriented programming?" And folks, I haven't changed one bit. Okay. Okay. We don't have a page fault handler. So by default, if we page fault, we're going to get a double and triple fault. Oh, it's time to live code! Woohoo! Ah, this is the fun part. Okay. I don't really like it on that side. Don't I usually do it the other way? Ah! Okay. All right. Okay. So I have probably a version of the OS here. Look at this, folks. Hey, you all seen that, right? The hello world, nice little hello world. And then how do we get out of there? Control to quit, right? Okay, and so let's go ahead and let's put a page fault in here. Okay, so how are we going to do that? I'm going to copy paste this because I don't really want to type all that. But what's this do? Okay, so you all know how computer scientists like to be clever. So they found out you can spell dead beef in hex, right? Which is like, it's like, you're dead meat, right? Very clever, folks. You could just put a 0 here. You don't have to say dead beef, right? Like, also, beef by definition is dead, right? So this is redundant. It would be really interesting if you had live. Okay, I'm done. Okay, so it doesn't really matter what you cast this to. In fact, I would argue that this is a low-grade type error because this should be an I32 because that's the default integer type. No one asked me, but that's what I think. And we set that equal to 42. Now, okay. This would be fine. That's fine, right? But what happens then? Then you get a line break, right? So that's bad.
Well, it's able to type infer what it is. So why would that be a type error?
It's a type. Oh, it's not a Rust type error.
It's just a.
It's a style type error. Yeah. Okay. Every time I see an integer in Rust, I type error because I think it's a U64.
Okay.
And then
that would probably be a reasonable default.
You don't have to defend them. After all, I'm the one that made the decision without any duress that, I don't know what it is. Let's cargo run. Oh, fun fact. Something I do with the test harness causes text to stop showing up in my terminal.
Other people have experienced that as well.
Which I like to refer to as the cool zone. So we're going to try and stay in that zone for the rest of class. Actually, it's probably bad for teaching.
Yeah. Why?
Okay, whatever. Wait, if I type L, it does the same thing as ls? Have I always had that alias? Did you all know this? Are you seeing that? Okay. None of you were going to tell me? What happens if I type C? Okay, the C is not found. Okay, CD is not default. Okay, whatever. What are we doing? Oh, we showed this. Okay, so panic, misaligned pointer dereference. Wait, that's why they didn't know it? Okay, hold on. Wait. Oh, it's perished?
We're in the cool zone.
Yeah, I forgot we're in the cool zone. That's okay. All right. So you can only do this with a U8 because of the F. Any of you heard of dead B? Oh?
Sure.
There we go. Okay. That is a reboot loop. Okay. Now, I kind of want to show you one thing, but it's going to look really crazy on the stream, okay? So, the way I read this stuff when I get these reboot loops is I turn on my screen recorder and then I pause it, okay? Because it's really hard to screen dump at the precise time. So you can do this in this class relatively easily because we can come, okay, I'm sorry to anyone watching this. Wait, okay. Pause, okay, right? How do I ambignify this? Oh, wait, okay, so that says CBIOS version 1. Debian. I think that's IPXE. This is kind of hard to read. Well, no, you can tell what all that is. Booting from hard drive, booting first stage, booting second stage. Okay, and then what happens if we advance by a single frame? And I think it's just popping that up slowly, right? Wait, no, we're definitely missing one frame. I can't get it. Yeah, sometimes it's going a little bit further. But, okay, anyways. If you ever are in a reboot loop, there's an obvious solution to that problem, okay? And that solution is to turn on your screen recorder. I'm sure this all makes sense to you. Okay. Or I should stop this. Control Alt to quit. Okay. Okay, so what do we do? Sorry, I will leave the cool zone. I am leaving the cool zone. Now you can see what I'm typing. Okay. This is extremely boring, but what we're doing here, I'm not allowed to write to this address, so I do some Rust so I can treat it as a writable address. I write to it. I enclose that in an unsafe block so the compiler lets me try it. Obviously it's unsafe, that's why it's in an unsafe block, right? And since I intentionally wrote this to be unsafe, it causes a page fault, and then things go down. One term I introduced on the site, virtual addresses and software visible addresses are not like literally the exact same thing, but this idea of software visibility is something to think about, which is there can be values in registers on your computer that you cannot see as the operating system. That's totally fine. There's no reason for you to be able to see those, right? And so that can be, I mean, anything in the internals of the MMU isn't going to be visible to you because you'd have to read it over a bus or something, right? So when we're writing an OS, we're not necessarily going to be able to see everything. But there are things we can see, and the things we can see are basically memory addresses that we can read and write to, and then there's also port mapped I/O, right? So this is deadbo is software visible because I wrote some software that's able to see it. That's what it means for it to be software visible. Okay. And this slide also contains the term key value storage, a recurring topic. Okay. So I'm not allowed to write to that address. Obviously, there's all kinds of addresses you're not allowed to write to. Let's just check one other one, because again, I'm not sold on this dead beef thing being as clever as everyone wants me to think it is. Let's just try and write to 0. Cargo, run. Oh, it's a null pointer dereference? That's why you can't do it? Okay. I'm just going to quickly allow a null pointer dereference here. Was it deref?
Probably.
Why is deref null pointer? I wasn't even close. Hi, deref. So I hear if you have a language server, you don't have to do all this stuff. But I'm not about to try. Oh. Wait, no, that's a different... Okay. Never mind. Surely I can put any other address in here. If I put in 4, is it allowed? There we go. Okay, so we are clever enough to pick other numbers, right? So you can't do 0 because it's too special. You can't do things that are potentially valid. Does anyone remember the address of the... Yeah. So we are allowed to write here, for example. I don't know how close to this we have to get before it stops exploding. But, yeah. Okay. So, steps. Let's pull up source main again. Here's main. We are in this line. Okay. Step 1. The CPU tries to write to dead beef. Dead beef is on initialized memory, so it hits a page fault. When you hit the page fault, that is a hardware level page fault. The OS asks to do something that it doesn't know if it is legal or not until it happens. Hardware looks up that address and says, we don't have anything for this, right? We're all sold out of dead beef. We only have living beef and dead cow. And so because we only have those two things, I have to call my manager, who's the page fault exception, okay? So the hardware looks up at the interrupt descriptor page, and it sees there's no page fault handler written. How do you know there's no page fault handler written? I will show you. We can look at our own interrupt descriptor table that we wrote ourselves. Here it is. Here's the interrupt descriptor table. And we only have a handler for breakpoints. So we do not have a handler for page faults. So, there's no handler there. That means a double fault occurs. Okay. Then we do the same thing. We see there's no page fault handler, so we instantly look up a double fault handler. We can't find a double fault handler. So, a triple fault occurs. Triple faults are fatal, so we perish. Now, perish here just means QEMU is going to keep trying to reboot you. That's all. So, to prevent the triple fault, we need to do one of two things. We either need to write a page fault handler or a double fault handler. And we're going to write the double fault handler first for the teaching reason, not necessarily for the programming reason. It's also probably good programming practice, because we are going to be issuing other types of tests to our OS that are going to cause exceptions, and we would rather those exceptions hit our double fault handler than some system reset loop. So we're going to write the double fault handler now, and then we can begin working on other exceptions. Okay, so let's start with the double fault handler. I am showing you both on the slides and on my screen my current circinterrupts.rus. I cargo fumatted this. Fumped, I guess is how you would say that. And I really hate how it looks, but it is does in fact fit on the screen. So kind of how ugly the new lines look are immaterial compared to the fact I can actually see it. So in case you're wondering what is going on, this is one of the most heinous things I've ever seen right here, but it works, so I'm reluctant to complain about it. Okay, so we're going to write a handler, and for now it's just going to panic, or I mean it doesn't even matter. There is one corner case to deal with. Let's open. It is so much harder to write code in front of other people. Okay. But it's character building. So let's go ahead and see, like, why did I scroll down there instead of hit Shift G? I could have done that in a single keyboard shortcut. My brain doesn't work when you're watching me. Perhaps, so I still don't know if those like people that are going to observe us are going to come. I think like you should all like politely close your eyes for the entire 90 minutes and not see what's happening. We should just see what they say. Can we? Never mind. We shouldn't prank the other professors. They're trying to help me be good at my job so I can help you be good at your jobs. Okay. What are we doing? Oh, I'm writing an exception handler. So, fun fact about exception handlers, they're like kind of all the same. So, we're just going to write a double fault handler here. That's not what I wanted it to do. Okay, any Vim geniuses? I want a Vim shortcut. So I typed DE there, right?
Yeah.
I want it to also stop at underscores. Right? I don't know.
DT underscore?
Okay. Double. I think I just called mine double handler. The double handler, or thank you, if I didn't say that. The double handler is distinct in two ways. I think it takes an additional error code, and then I think it also has to be a diverging function. Let's see if I can remember how to do this. Oh, and also I should not say exception breakpoint. I should say exception double fault. Yeah, woo, exciting. Okay, let's see. See how close I am. Right, we also have an error code. This error code is a U64, a completely reasonable default numerical type. Okay, so we have an error code U64. Okay, and I'm going to say something. Why am I going to say this? Okay, I have an opinion about software development practices. The blog, which is cool, right? The blog has you write this with the underscore prefix on error code, right? I've been underscore prefix opinionated previously. Let's see. Okay, what's wrong with this? Sorry, we have to fix this. Unexpected closing delimiter. Do I not know how to write diverging functions? Does it have to be on its own line?
It's because you have two end parentheses.
I have two end parentheses. I do see that. It's the new lines. It's the oh, because I'm not panicking in there. Just a sec.
Make double handler.
Oh, this is supposed to be a panic. We ripped the panic. Okay, this will work now. Cool. All right. Cool. Right. So quit. And it's source interrupts. Okay. So I got this kind of crazy idea here, where you definitely shouldn't ignore the error code because it should always be 0. This is a handler, and my sense is you shouldn't make assumptions that strong, right? Because maybe what caused the exception is like internal inconsistencies in your bit storage or something, right? So I think you should do this. I think you should assert that the error code is equal to 0. Assert is a macro, so I assert exclamation point. And then I think I haven't shown this yet. It is certainly my preference to write asserts this way, because I'm used to them. But there's also assert eq, I believe. And I can assert that these two things should be equal. So my sense is you should not be ignoring error code arguments when they're provided to handlers. The whole point of your operating system is it's supposed to deal with error handling. So let's see if this works. Ah, beautiful. Another triple fault. Okay, so wait, why are we still triple faulting? Students, you're smart. Why are we still triple faulting if we wrote a double handler? Wow, it's like it's eerily silent in here. It's like a graveyard during a snowstorm or some other very quiet time. You know, because snow deadens sound so you can't hear the undead. But I guess if they're undead, they probably already left the graveyard. So, speaking of leaving places, did you any of you put your double fault handler inside your interrupt descriptor table? I bet you all didn't do that because I didn't do that, right? So, okay. Here's where I set the breakpoint handler. So I'd probably say idt.doublefault.set handler fun double handler. And double handlers are not to be confused with double handers, which is a weightlifting grip, maybe? Double overhand, that's one. Double hand, I don't know. Okay. Sometimes you gotta put yourself out there and it doesn't always work. What? Did you see that? Okay, I'll do it again because you weren't watching. I watched you not watch. Okay, so here's my, oh, it's a double fault. See, it's a stack frame dump. That's exactly what I want to happen instead of hitting the triple fault and going into a reboot loop. So we're probably all feeling pretty accomplished, right? And we should be. Well, I'm proud of us. I'm going to cargo format this. Cargo format. And what's this look like now? Okay, yeah, so I guess this is how you're supposed to write diverging functions. They get... Okay, so cargo format, comma terminates the last argument. So this is like a JSON comma, and then it puts the paren on the next line. So that's, I don't know, I do think that's cleaner than what I did. And you see I have the two different types of asserts here. Okay? All right. We add it to our IDT, and now we're going to test it. Okay. So I had this problem where I wanted you all to be able to see this if you didn't come to class today, right? And I appreciate you coming to class, but I also want you to be able to check these notes at home, right? And so I have previously showed you a few ways to get things out of QEMU, and I want to show you one more. And I think this one you already know how to do. I'm just pointing it out from like a systems design perspective. So obviously I can screen dump this. We understand that, right? But what if I just want this text, right? And so we can get this text without doing the screen dump, ppm to pmg, base64 HTML pipeline. And the way I'm going to do that is I'm just going to go through the serial port. We've previously configured the serial port to work for moving internal information about our emulated device to our host device through an emulated serial port, and then it shows up in the terminal, and the terminal is text formatted instead of image formatted, right? So this could be a nice thing to do. And so the way I'm going to do this is I'm going to begin constructing my testing functions, and I'm going to claim once again, wow, in this case it really does make sense to have a testing framework, okay? So you can be a test hater like me and you can still use a testing framework. So I'm going to start with should panic, and the reason I'm going to start with should panic is let's take a look at should panic. What's this thing do? Well, it triggers something an awful lot like an exception, then deals with it, right? And that's what I'm doing with my double fault handler. So I'm just going to take this, I'm going to port this over, and I'm going to modify it a little bit. So we're going to take should panic, and we're going to make a double fault.rs double fault handler test. Let's go ahead and pop that open. What do we want to do here? Well, the first thing we want to do is we want to cause the same type of fault that we're causing in our run environment. And we already have code that can cause that fault in our run environment if it's over in main. So I'm going to go ahead and grab that. I'm going to pivot to main. I'm going to go over this. Oh, cargo format split it onto multiple lines. Do you see this? Okay. I'm going to get rid of allow null pointer. I'm going to visual block this. I'll yoink it. This thing was called test double. And I'm going to replace my bad thing. So previously I caused a panic by asserting false. Now I'm going to cause a double fault. Well, I'm going to cause a page fault, which will then itself cause a double fault by doing looking up something that doesn't exist. Okay, so we're going to go ahead and do that. Now, the only other thing to do here, well, let's run this test real quick. No overwrite since last change. No write since last change. Okay. I'm going to go ahead and run this, and I'm going to run this. I could run it with cargo T. And, folks, I've written quite a few test scripts, like more than I'm like super duper interested in running all the time. We're back in the cool zone. See that? Cool zone detected. Okay. Yeah, see, that's what I typed. Oh, wait, no, the whole point of this is to show you what I'm typing. Okay. Cargo T, you can specify a test, and I'm doing the double test right now. So this is much faster. I can just get one thing here really quickly. So, not great and not terrible here, but one thing I do want to point out is that I am successfully initiating a test. So, what are we going to do from there? Tests double.rs. Okay. So, first thing to do, I would like to point out, and I think this is non-obvious, but I do want to point this out. We are now using an initializer function, and let me show it to you in two places. In source main, we use Osiris init. I'm going to yoink this. And in lib, we wrote our init somewhere. Okay, it's right here. So right now all this is doing is this is setting up the interrupt descriptor table. But importantly, unless I do that, I'm not going to be using the same interrupt descriptor table I wrote in my testing framework and in my running framework. So I need to do that inside my tests. So we'll go back to the tests, and we'll put our initializer in there. Okay, let's punch out of here, and we'll run this real quick. Okay, no problem. Wait, that actually worked? I guess it should work, right? Yeah. I did the thing I'm supposed to, which is I hit a panic by page faulting. Okay. This isn't quite the problem I'm trying to solve yet. Here, let's move over a few slides. Okay. So, test double. Okay. What I want to do is I want to see that stack frame that I was looking at previously. And that's no problem, because that stack frame I was dumping, I was just print lining the panic info, because that's what my panic handler was doing. So I'm going ahead and do the same thing here. I'm going to Osiris serial print line, and then instead of printing pass, I'm going to like debug print the info, maybe. And then I'm going to change these to not ignore the info. Maybe this is going to work. And with that, you can see the exact same text that you were previously showing inside QEMU inside your host terminal. And this is really useful if you don't want to try and type this number manually, which I did not want to do. Now, you can claim, Calvin, did you write an entire test suite just to not copy that number? The answer is yes. I thought it would be faster to write a test suite than to manually transcribe this. And I think that's probably what I have over here. Let's see. And blah, 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 blah. We've got a virtual address. Oh, I got more stuff here because I didn't just print the internals. So there you go. This is an extremely fun thing to do with your free time. And then, when you're done, you can just get rid of this line, change info back to ignorable, and then your tests work again, which is pretty cool. So we now have a double fault handler test. I think that's neat. Okay. On to the next one. Oh yeah, get this working on your own time. It's possible you were keeping up with me while I was doing that, but you should have one of these tests as well. Back to work. My throat hurts. Ugh. Is everyone staying healthy this season? Is everyone staying postureful and well hydrated? Okay. What happened? CPU tries to write to dead beef. That's not true anymore. Now it's trying to write to 100, which is also 256. That causes a page fault. The CPU looks at the corresponding entry in the IDT and sees that no handler function is defined. So it does not go to the page fault handler. But the only reason it doesn't go to the page fault handler is because we haven't written one. So it goes to the double fault handler. We've now written and implemented and provided and all of that stuff set up a double fault handler. We wrote the function and we put it in the IDT. That's our responsibility as the OS. That's it. So now, like me, the CPU abstains from dead beef and is vegan. You are not required to be vegan to participate in this class, and you shouldn't necessarily feel pressured by the fact that I make the correct lifestyle choices, okay? The triple fault And the boot loop. Boot loop. It rhymes with Fruit Loop. I'm getting destroyed up here. Okay, it no longer occurs. Okay, I'm going to redeem one of my distractions for the day right now. I have to know if Fruit Loops are vegan.
Our Fruit Loops are vegan.
I spelled Fruit Loops wrong? Is that really how they're spelled? There's no...
It smelled like Fruit Loops though, so we're winning in that way.
Yeah.
Wait, it's not fruit like the actual word? No.
There's no fruit in them.
I didn't think about that.
Never redeem your distractions, folks. It's a cacophony of horrors out there. Okay. Do you all have, like, any memories from your childhood? Yeah, this is
I
just...
hope so.
You hope so?
My
Okay.
earliest memories are when I was 3 years old.
I don't know if this is true, but I'm going to say something. I think my earliest memory is in Azeroth in World of Warcraft. Like, I don't know that that's... And it might be because I can't tell the order of things, right? So it might just be mislabeled. Like, I have to have learned to walk before I played World of Warcraft, right? Because it came out in 2005, and I'm old, remember? Okay. The triple fault occurs, I think we're fine. Complications. Okay. You're probably all feeling pretty accomplished there, huh? You know how to spell Fruit Loops, first of all. That's crazy. We still don't know if they're vegan, because we only got an AI summary. And AI is not even vegan, so how would it know, right? Okay, I have something I want to redeem a distraction on, but I don't think I have a distraction token right now. Okay, we caught the easiest double fault in the universe, which is we intentionally didn't write an exception handler for something, then triggered that exception. Probably this is not a good way to design an OS, right? Like, probably we should be like a little more rigorous than that. You remember the first time I triggered a reboot loop with my operating system was I wrote an infinitely recursive main function. You may remember this. What did I type? So, this is fine, right? But wouldn't it be a lot cooler if we went to infinity, perhaps even and beyond? Does anyone know if I have to specify return type for this? And then we go ahead and come in here, and we to infinity. Infinity. Why did I pick such a long name? Oh no, it's still a triple fault, but I was supposed to have written a double fault handler. What can calling a function be doing that's not even hitting the double fault handler? Well, let's stop this. Okay, I'm stopping it. Okay. So apparently Rust, allegedly a great language, even when it's infinitely recursing, it still keeps pushing like return addresses onto the stack, even though it's the same return address. I don't know why it does this. I'm sure if I wrote that in Haskell, it would not Stack Overflow. That's what I'm saying that 100%. I think that's because it's lazily evaluated.
Probably.
Okay. And I am also lazy and evaluated. So that's two good things. Okay, so I'm not lazy. That's great. I'm not evaluated either. Okay, I'm neither of those things, actually. Okay, so before we look at the special cases, we need to know the exact causes of double faults. I've been drilling on this for a while. So the first I was like, it's an exception when there's another exception. Then I was like, it's an exception there's not a handler for. Neither of those are true. I've been lying to you the whole time. Why am I doing that? Because I don't actually have all the special rules memorized, so I just put them in the slides, and I don't think they matter. Okay, so here are the failure cases. What does fails to invoke mean? So it means the handler might not be present, but it can also mean this like weird thing called the handler is swapped out. So when things are put in memory, they usually go in RAM, and they usually come out of the hard drive, historically now the solid state drive, and go into RAM. Sometimes you're using all of your RAM to store your Verilog compiler that I'm using for research, or whatever it is you use RAM for. What's something that's RAM intensive? Video editing, probably? Like, I don't know. Okay, so you're doing some video editing, you're watching Ghost in the Shell, and you're like, I can make a better version of Ghost in the Shell myself. So you load up a large language model, and you ask it to make a better version of Ghost in the Shell. And that's how they made the 2017 film starring Scarlett Johansson. Come on, that was a good one. That was a banger. No one laughed for that. Okay, so
That made me laugh.
see, I knew I'd get someone. Okay, thank you. I can't give extra credit to people that laugh at my jokes, or this class would be much worse than it is. Okay, what happens if a handler causes exceptions itself? Okay, I have to introduce swaps. Swaps are, I didn't really think they were a 1960s topic, but if you think about it, it's like, oh, that's when they were writing Unix, and so this is probably the first time they dealt with this problem. Having RAM is kind of like a cool new thing. It's not that new anymore, but it is the newest thing because nothing has displaced RAM. And so you introduce random access memory. It costs a fortune, so you buy as little of it as you can to do basically one calculation at a time, right? That means every time you have to change between calculations, you have to swap things out. Also, my understanding that if you go far back enough in history, they were physically swapping memories around. So you were like taking tapes in and out, right? That kind of makes sense with floppy disks. What does this mean? Well, in this case, if I have, for example, a program on it, I'm guessing it was a magnetic tape at this time, and I pull it out of the computer, the internals of the physical computing device, so all of its registers, are still set in a state assuming that that tape is placed inside, unless pulling the tape out triggered some exception that reloaded things or something, right? So anyways, somehow you can physically swap things out of memory, right? And it doesn't update the processor state. So the processor state can be referring to memory locations that, for all intents and purposes, no longer exist. That's, potentially bad. Okay, fast forward. These links are to history. This is Wikipedia. This is going to the Red Hat documentation, because this was my first Google hit. I ran into swap space on Linux, and I gave a real example. It was when I was simulating devices, and I tried to boot Linux on them, and I tried to log everything, and it filled my hard drive. But before it filled my hard drive, it filled my RAM. And so the first error I experienced, the first time I filled my RAM, was I got a little note from my operating system that said, hey, we blew up your RAM, and then we blew up the stack space, or the swap space. I bet this problem will go away if you just give me a bigger swap space. So of course what I did is I created a swap space that was the same size as all of my physical drives put together. And this is how I filled my hard drive. So the operating system was then authorized to write things from RAM directly to my hard drive to cache them locally. My understanding is there's a few things around that this increases your performance for. I think one of them might be like a video game benefited from a swap space or something. This isn't too crazy to me because I've seen video games that have load screens that are long enough you could read something from a hard disk drive into RAM and back. So you might be able to do some like hijinks with working memory or something there. And I'm guessing there's other applications. And as soon as you're asking for memory-intensive applications, once again, I'm reaching for video editing. So I use DaVinci? Does anyone know the big video editor?
DaVinci Resolve.
DaVinci Resolve. Yeah, I use DaVinci Resolve. And it's so slow and low performance. And I think that's just because it's dealing with a bunch of bits. And I'm not about to write my own video editor. But I do get the sense that like if I'm editing like a 70-minute long high-definition video and I'm like clicking around with it in a bunch, I think it's moving stuff in and out of RAM all the time. And that's why it seems really slow to me compared to other things I'm working with. So I'm guessing that's some notion of swap space as well. Swap space is located in a hard drive, slower access time. You can use a dedicated swap partition, a swap file. I think I used a swap file, I don't remember. Right. So you can set up swap spaces on your device. I haven't had to do this manually for years. so I don't actually remember how to do it. But you'll see I have a swap. And this is as default as they come. Like, I took this computer out of the box and I put Ubuntu on it, and then I left it at the office, right? Like, this is not like a Calvin setup computer. So I got a little swap space here. And I guess you can look at a swap file. Or I guess this is a metadata swap file. So yeah, I have swaps set up on my device, and I didn't set them up, so someone set them up for me, so this is just the default swap. And you can check this. Presumably, Microsoft Windows uses swaps too. I don't know.
Yeah, basic all operating
Yeah,
systems
I think
use
you
swaps.
have to. Like, your device would feel like it doesn't function without it.
Yeah.
It's one of the things that makes it feel like we have infinite memory.
Yeah.
How to increase the size of your swap file. This is, I guess, an Arco Linux thing about
It probably works for other
Ubuntu?
stuff. It's going to be for Arch Linux.
we use an article for Ubuntu. Yeah, I don't know. And do whatever you want.
It probably works across all of them.
I bet it works across all of them. Go to the Quad Center and bother a Linux lifestylist. Yeah, that is funny. I still think one of you should get really into FreeBSD just to bother the quad tutors. I am encouraging this strongly. The first one of you to get really into FreeBSD only to bother quad tuners, I will award 1 gold star. Your computer will never work again. So I don't know if that's worth a gold star to you. You also get really in. So the other thing that happens is every time someone mentions containers, you bring up jails. Because I guess FreeBSD had containers before everyone else, and they're very proud of this. Okay. What if a breakpoint exception occurs, but the handler is swapped out? What if a page fault occurs, but the page fault handler is swapped out? What if a divide by zero handler causes a breakpoint exception? How would that happen? Well, if I have a divide by zero handler and I put a debug breakpoint in it, right? So if I'm debugging my divide by zero handler, this is exactly what would happen. You are about to write a divide by zero handler because you're writing an operating system, right? So this is a real thing that could happen to you if you use debuggers. And for the sakes of appearances, we're trying to maintain to the other people that are judging us to see if we know computer science, we're pretending we use debuggers all the time, right? Okay. What if your kernel overflows its stack and the guard page is hit? So your stack is not actually infinite in size. At the top or bottom of the stack, depending on how you visualize it, there's a guard page. When you start writing stack to that, something destroys you. And specifically, that's supposed to raise a certain type of exception. Okay. So the blog links the AMD 64 manual, and we can just look at this real quick. It's a link to a PDF. You can see at the bottom of the screen how it says PDF there. I bet this is a real PDF. Oh, it's a link to a place giving me cookies and has a search bar. Oh, that PDF we can't find it anymore. So my recommendation to you, just assume whatever hardware you're working on at any given time does not actually have a manual. This has made me very happy in life. You can always just figure out what it's doing. But anyways, I thought I would point that out. A double fault exception can occur when a second exception occurs during the handling of the first prior exception. Here's the table. This font is small, so it fits on one screen. Sorry about that. But I formatted this a little bit so it would look more obvious to me. And what is that? We basically have this family of 4 faults. Invalid TSS, segment not present, stack segment fault, and general protection fault. Those are kind of all one exception, which is they're all problems with a segment. So I think of that as the segment family. So when you see this collection of 4 in 3 places, just think segment family. Okay. So if you have a segment family fault or a divide by zero, and you hit another segment family fault, then you double accept. If you have a page fault and you hit a second page fault or a segment family, then you double accept. What do these all have in common now when we look at this? Well, divide by zero seems a little bit far out. The other ones are all about memory management, right? So mostly what's happening when you double fault is you're dealing with a memory problem. How does divide by zero fit in here? I have my security hat on here. The reason divide by zeros keep me up at night is because I suspect that whenever divide by zero is occurring, you should wonder if that is an attack on your system of some kind. Perhaps where an adversary is trying to load certain values into certain addresses, or detect if some value is 0. Right, so I can guess an address of something, perform a subtraction, perform a division, and that will tell me if I got the two numbers the same, right? And it will tell me not by populating registers, it will tell me by the behavior of the device changing, right? So my thinking is that the reason you treat divide by zero faults as a memory fault is because in the worst case is it's an attacker attempting to do something to memory. So you regard it as a memory problem, even though it's not necessarily a memory problem. It looks an awful lot like an arithmetic problem, but a lot of arithmetic problems can become memory problems if you're doing pointer arithmetic. So that's how I think of it. So we now know what happens in all cases. Okay, if I have a breakpoint inside my, not what I'm saying. That was the second example. If I have a breakpoint handler that's swapped out, that's a page fault. Why is that a page fault? Because it's swapped out, it's not in memory anymore. That's what a page fault means. Okay. If a page fault occurs and the page fault handler is swapped out, that must be a double fault because we don't have a page fault handler. So we bypass the page fault handler and hit the double fault. If a divide by zero hits a breakpoint, that's no problem. Why? Because we know the bad thing that could be happening, which is an attempted unauthorized memory access. That's not what's happening because we hit a breakpoint instead. So someone put a debugger inside your divide by zero handler. No one cares about that. That's not going to be a security problem, right? If the breakpoint handler is swapped out and then you run a debugger, you're going to hit a page fault. That's fine. That makes sense. We're just missing memory. No one's privilege escalating or anything. Okay. So the common case is you have an exception without a handler in the IDT, which is, what does the IDT stand for? Oh my gosh, you all pay attention. That's crazy. I asked my AI class what AI stood for. That's not true. I mean, I'm telling lies. They definitely know what AI stands for. I don't know why I'm slandering them. They're great. I did make them learn matrix multiplication today. That was mean. Okay, so all right. The thing that happens. Okay, exception. Deref the IDT entry. You can't deref it, so you general protect. We don't have a general protection fault handler, so you double fault. Okay, easy. And that can happen with general protection, where you try to read pages that are there that you're not allowed to see, and with page fault, where you try to read pages that aren't there that you don't even know if you're allowed to see them. Okay, let's look at the fourth question. What happens if our kernel overflows its stack and the guard page is hit? Oh, well, okay, all right. There was a lot of sleight of hand there, right? I showed you a large number of cases where you could get a double fault handler, and then I shoved one at the end that was conspicuously easy to trigger. Why did I do this? Once again, I am teaching a class. Obviously, we could construct these like lengthy chains of exception handlers, and you should do that in your tests if you're looking for something to do. But that looks pretty tedious to me, right? So we're going to do this in the easy way. We're no longer in the cool zone. We're now in the easy zone. And in the easy zone, we're just going to write infinite recursion. So what if the kernel overflows its stack and the guard page is hit? No problem. Guard page denotes the bottom of the stack to check stack overflows. Stack overflows, I think I've been told this, but I was told this like many years ago by people referring to a long time ago. I guess stack overflows used to happen all the time because it was really hard to write code that was memory efficient enough to run on devices at all. So the stack overflow like gained this notoriety as this like thing that you have to get rid of, and then like when you're a good programmer they go away because you just like happen to manage memory well through like years of practice. Now it's like impossible to cause a stack overflow, and they're only in the case of infinite recursion. Or like really large numbers of recursion. So I will semi-regularly write a function I expect to recurse 1,000,000 times, and usually the device doesn't want you to do that. Okay, so what is the guard page? First of all, it's not real memory. It's an idea. In this way, similar to like page mapped.io or something. So it's not mapped to a physical frame. So if you hit it, you explode. And explode in this case does mean page fault. We gotta shout out Rust when it happens. Really, you should have page options. That's what you should have. You should not just have pages and look. Okay, so if Unix was written in Rust, probably this would not be a specific type of problem we would see. You would still have to deal with the case that you can potentially run out of memory, right? But it would happen in a different way, and that's interesting. Since this is OS in crates and not OS in Rust, I'm allowed to shout out Rust and still be annoyed with this class. Because the bootloader, which we didn't write ourselves, we just assumed it worked. It sets up a guard page for us, and it didn't tell us, and we didn't think about it at all in 10L. It just happened to show up in class today right when we needed it for this example. So good job, bootloader. And why did we not write our own bootloader? Because it would take an entire semester. Okay, so page fault occurs. CPU looks up, whatever. I'm tired of this. Okay, I would like to remind you what the interrupt stack frame looks like. Why am I reminding you of this at this time? Doesn't that look kind of big? Right? There's more stuff in there than there would be in other things. So if I start blasting a bunch of interrupt stack frames, I'm going to chew up my stack quicker than normal, right? Quicker than normal? Quicker. No, it would be more quickly. Sorry. So if I'm chewing something up and I'm referring to that speed, chewing is a verb, so I should modify it with an adverb, not an adjective. Okay. I would like to issue a correction to my previous sentence. On the second page fault, the CPU, okay, get page faults, okay. Page fault, push a stack frame, page fault, push a stack frame. What happens? One of the stack frames overflows, hits the guard page. You hit the guard page, you call the page fault handler. The page fault handler pushes a stack frame, or the double fault handler, because we don't have a page fault handler, pushes a stack frame. That stack frame hits the guard page again, that escalates to a triple fault. Let me show you an example of this. That's it, right? I have a stack overflow. Is this all making sense? Am I going too fast or too slow? That was a trick. You don't go fast or slow. You move rapidly or slowly, okay? Don't. I know what adverbs are. Okay. And the way we're going to do this is it is time to make a new test. So I showed this in main. Wait. No, I'm in the cool zone. I'm in the cool zone again. Look. Oh, no. Okay, I'm not. Okay, we're fine. I thought I was in the cool zone. Okay, so we're going to make a new test. Except, I don't know, I'm starting from except. That's fine. No, overflow.rs. Remove tests ov. Okay. What do I want to do here? Okay, so what I want to do here, we previously wrote this to test the breakpoint exception. No problem. We're going to get rid of that. We're going to do something else. We are going to go to main. We're going to grab to infinity. We're going to yoink. We're going to switch to tests. It's this thing called overflow. We're going to put in our function. And then we are going to call to infinity. Okay. Now I can cargo t test overflow and get the expected problem. I should probably, because I'm planning on running cargo test at some point in the future, I should probably add this flag to it. This is the unconditional recursion allow. We've seen this previously this term. So we will allow unconditional recursion, maybe. No, I did something wrong. Allow unconditional recursion. What did I do wrong? That sure looks correct to me.
You unconditionally cursed.
But I say I'm allowed to do it.
Yeah, and it did let you.
Ah, okay.
Or did you spell infinity wrong?
I spelled something wrong. Oh, okay, yeah. Infinity, nope.
I feel like there was something that would like detect that before you compiled it and help you.
Do you think like a language server would do that?
Yeah, something like that.
Unfortunately, this is not a servers class. This is an operating systems class. Okay, so looks like I'm getting the same error to me. Am I making this up? Okay, I'm going to copy this.
No, the error is just that the tests are failing.
Well, I don't want a compiler warning.
Okay, well, but you get rid of the compiler warning too. Yeah.
Is this not what should do that? Does this not?
Should.
Yeah. I don't.
I think you need it at the call site, not on the function.
Oh, at the call site? Okay. What did I call that file? Overflow? I will move it to the call site.
There's technically a way to do that.
No way! How do I get rid of that warning?
You didn't move it to the call site. You made it global. I think call site in the function, in the infinitely recursive function.
Okay.
That's what one above function would work fine.
Wow.
What is wrong with me?
Maybe try both.
I'm putting it everywhere, folks. What am I supposed? Is it not allow?
Did you spell it wrong?
I have to. But I don't see how I spelled it wrong.
Yours is working.
Works fine. It looks the same.
I think your computer just hates you.
Are you remembering to save?
It has to be, right? Yeah. Like, it looks pretty allowed to me. Like, if I were doing code review on this, I would be like, this person really likes unconditional recursion, is what I would think about this. Let me check the answer key. No, GitHub cd rs work. Okay, yeah, this did work on a different computer. I did name it Recurse. Can I add something to Cargo Toml?
This is the linter, so you'd have to have a Clippy config. I don't remember how to do that because I don't ever do that.
Cannot return without recursing. What if I do mutual recursion?
Maybe.
This is not related to class, but I'm annoyed. So obviously the and beyond here. It's only hitting one of them. Okay, so fun fact, the error was in main the whole time. Okay, so it did work.
Yeah.
Here's something you should learn from this. When you see a warning, it is helpful to check where it is. Because in fact, this entire time I was referring to a different file than the one we were currently editing. What have we learned today? That can't be right. I'm going to keep the mutual recursion though, that's kind of cool. I think it would also be slightly more cool. You all heard of this thing? Instead of writing an actual infinite function, you should just write something that's practically infinite. So you just write the Ackermann function, and you just give it like enormous numbers, and it has really poor complexity. So that would be way cooler. I should probably keep teaching. Okay, so allow your unconditional recursion. Step 1, any great language allows unconditional recursion. Okay, that's how you test it. How can we avoid this problem? Okay. We should be feeling a little boxed in here because the way to solve this problem is someone else has cheated on our behalf. Okay, so There is nothing I can do at software level as the person writing the OS to prevent a stack frame from being pushed. It's a hardware reality. It's implemented that way. There's nothing I can do to prevent the exceptions from going out. I can't prevent every double fault, right? So like I have no control over this at all. So somehow I have to be able to find a place that I can safely push a stack when an exception occurs. But this is not the craziest idea in the world, because I'm already an operating system kernel, and probably my operating system sometimes is going to run software at user privilege level. And so there's probably already going to be multiple stacks floating around in my system somewhere. So the x86 architecture is aware of this, and it simply maintains multiple stacks. Now, would I have solved the problem of your stacks taking up too much space by having more than one of them? No, but I don't know of a better solution than this, so I guess I probably would have reversed engineered myself into like, oh, we'll just keep a backup stack that's always good. And is it really always good? No, because I can write an infinitely recursive function inside my handler. But what this means is that if I don't write anything that blows up my stack, then the stack will never be unrecoverably blown up by software. So I can still cause the same problem that software does to me, but if I make sure my own OS isn't going to cause those problems, then I'm safe. So this is like this kind of bizarre level of quality that we're arriving at here. Apparently, there's 7 of these interrupts. There's an interrupt stack table. There's 7 of them. I don't know what that will correspond to. I don't really care. It's in a table, so it's some kind of linear data structure. So how are we going to do this? For each exception handler, we get to specify one additional thing, which is we get to specify which of the interrupt stack tables we are going to use. And we're just going to do this by indexing into the stack pointers field in the IDT entry. Probably can look at interrupts somewhere. So there's these IDT entries, interrupt descriptor tables. This is some kind of data structure, right? So we can configure these data structures to use different stacks, okay? I want to point out, I don't know if this is 0 or 1 indexed, because there's a lot of references to the first stack in the IST, and this is also based on the PDF that I don't have a link to anymore. So I don't know what first means, and that's fine. Fun fact, this is a hardware-supported feature. That's good it's a hardware-supported feature. This is basically debugged hardware, where there was a case where hardware could cause an error that software couldn't recover from. So hardware exposed to this API, maybe we shouldn't call it an API. I don't know, exposed to these features that software can now use to deal with what would otherwise be an unrecoverable hardware problem. So it's a debugged hardware-software interface. We're going to use the TSS. What I would like to have happened is when I gave that name, you inferred from the name that it is probably referring to some kind of register. That's because it has a 3-letter name and it ends in S. And my hope is that this looked somewhat familiar to you to the CS code segment, the DS data segment, and the SS stack segment. Now, if that didn't happen, don't beat yourself up, because it's already weird that it's called the TSS instead of like the TS or something, right? So don't worry about that. This is the task state segment. It is no longer used for task states. That's fine. There were different ways to try and solve this problem in 32-bit architectures, and those ways of solving problems did not extend well to not really just 64-bit, but actually the version of 64-bit we have now, where there's a bunch of architecture extensions going around all the time, the most prominent of which is the vector operations, but now there's a lot of things with virtual memory for cloud. Okay, so there are always jamming more stuff into the architecture, and since they're always jamming more stuff in the architecture, that means there's more possible corner cases you can deal with if you're trying to do hardware context switching. So hardware context switching, you're saying, we're not doing that anymore, software is fast enough. Context switches can be brought to a minimum, and so we're not going to worry about hardware context switching, but these names that might be like poor rhymes are going to end up being used. So what is the task state segment? It's just something we use for this. This is what it looks like. This is the 64-bit version. That IO map base address, that is shared with the 32-bit version. And you know what the I/O map is because you've used port map I/O. What did you use it for? We just used it earlier today. That's how we interact with our serial ports. So that's around, we've been implicitly using this. Then you have an interrupt stack table, and you have a privilege stack table. Absolute geniuses will probably be able to correctly guess what the privilege stack table is. There's different privileges for things running on your computer. We've seen this before. So there's user and kernel. So there's going to be a kernel stack table, and there's going to be a user stack table, right? Why are there 3 of them? Good question. Why are there 7 of them? Great question. These are both powers of 2 minus 1. That really makes them feel 1 indexed to me. I don't know. But I don't think that privilege stack table is 1 indexed because the kernel has privilege level 0 and it's almost certainly indexing it at its own privilege level. So I don't know what's going on there. Then there's a bunch of reserved bits. Why are the reserved bits? Well, really this was an alignment problem with the old TSS. So the segment descriptors have to be a certain size, so you just reserve a bunch of things. Okay. One other thing that's pretty weird, I mean, there's a lot of stuff that's pretty weird about this. These are 2 64-bit fields that are offset by 32 bits. So these are misaligned. I don't know why they did that. I'm guessing it's a security thing. So it is very, very difficult to hit these by accident. And it's probably pretty hard to hit them on purpose as well. So I don't know, but that looks like this reserved 32 bits, that really looks like they're trying to offset this so people can't use this thing. Because you don't really want someone to accidentally jump to a multiple of 64 and it'd be the kernel stack table. Okay. Some of you have heard of PST. It's not a time zone. A lot of people think that stands for Pacific Standard Time. It's this privilege stack table. One thing to review on this slide. This doesn't matter, but I would like you to know this. Privilege is defined in the code segment, the CS. Within every segment descriptor, bits 12 and 13 are the descriptor privilege level. These 2 bits are always the same in practice, but nothing in hardware is enforcing them being the same in practice. And if you write your own OS, you can keep them to not be the same in practice. By write your own OS, I do not even mean what we're doing in this class, because the x86-64 crate is going to force you to keep them the same. So you have to go 1 level lower than what we're working with. This is going to be manually setting individual bits with assembly instructions, right? No one's going to do this, right? But an attacker could. There could be a security vulnerability here, right? So the code segment has bits 12 and 13, and they are either both 1, which means you're not privileged, or both 0, which means they are. Okay. We can imagine what happens here. I'm just going to sketch out an example. Unprivileged executable divides by 0. I just did that, right? You saw me do that with Python at the beginning of the class. Handler is called. The handler must be privileged because the handler is part of the operating system. It has to do OS stuff. So there has to be some privilege escalation. When the privilege escalation occurs, you need to switch to the privilege stack, because the privilege stack might have stuff on it that only the operating system is allowed to see, like the location of the interrupt stack table, IST, IDT, all these like 3-letter things, right? Okay. This is stack 0, since privilege 0 is the most privileged. It is a little bit weird to me that when the privilege bit is set to 0, you have privilege. I would not, that didn't make sense to me, but it's fine. So just try not to get too confused. The way I remember this is there are phantom privilege levels, -1 and -2, that are omega privileged, that can preempt the OS. So I just remember negative things are like extremely special, and then I remember 0 is the lowest privilege. Okay. We're not going to worry about this for now because software is not running on our OS yet. We're going to create a TSS. Oh, I'm running out of energy. Stretch break. You don't love that. This is like the cool part of x86.
It's cool, but it's just so much. Just built on top of itself
Yeah.
again and again.
I really respect that they reused a depreciated 32-bit register for this, right? Because they could have added new registers, and they were like, we're getting rid of that, but we need to have this GDT. We're going to make it work.
Yeah.
And I'm pretty sure I really like that 32-bit offset. That looks like very good engineering to me. So like none of the default versions of any instructions that divert control flow can read that table.
Yeah. which is very
That's
similar.
like an extremely high degree of protection. I don't think anything has that level of protection.
Yeah.
So yeah, okay. Let's make a new TSS. Tasks state segment. Got it. First try. Okay. We're gonna make a TSS struct, and by we, I don't mean we at all. Yeah. I'm cool. So I feel like every time I say that I lose cool points. I'm self-aware. That's definitely not true. Okay, I made a source GDT. Why did I do that? Right. Okay. So I'm gonna make a task state segment. The task state. These words are hard to say, by the way. The task state segment is a segment descriptor. Segment descriptors live in the global descriptor table. I am pretty sure I'm going to have to write a global descriptor table at some point. So I'm going to create the file for the global descriptor table. Goodness me. And then I am going to put the task state segment in there. I don't feel like I usually struggle this much. It's the SK at the end of task. Okay. All right. So what are we going to do? I don't know why I open source GDT first. Well, that's fine. Okay. Let's go to lib. Something I like to do for fun is, as a user-level user of my device, I have permissions to read, write, and edit this file called lib.rs. So I like to refer to that as me owning the libs. Isn't that fun? Okay, all right, I'm moving. Okay, so I'm going to create a public mod for the GDT. Sorry, I was hanging out with my younger siblings this weekend, and they watch clips of Alex Jones all the time. But they do it ironically, so it's okay. I think I'm like trying to get them to do other things. So we're gonna run ultra marathons as a family now because that's what I came up with. But anyways, my brain works. Okay. What am I doing? Okay. So I'm gonna create a GDT mod. And it's going to have an initialization function in it, and it's going to be very similar to interrupts. In fact, I'm going to save this, and then I'm going to open interrupts just so we can get it refreshed in our minds what it looks like. So we have a static mute that is an x86-64 crate. We have an initializer function that has a bunch of unsafe in it because it's modifying the static mute. Blog wants you to do this with lazy static. Maybe some of the Rust people wanted to do this with lazy cells. Is that true? I really like static mute hue, but I don't know what lazy cells are. So.
I didn't bother using one for that.
Okay. Then I have a series of local things. They happen to be functions in this case, but I have local things that I'm loading into the static mute. Okay? We're going to do basically the same design pattern in the GDT. Okay, here it is. So one of the things I know I need to do, I need to write a public function init GDT. That's going to do something in it, and that thing is definitely going to be unsafe, whatever it is. Okay. I'm going to need a static mute. That static mute is going to be a GDT. What type is it going to be? Oh no, so at this point we just check the notes and we go on and we say, okay, what we need is we're going to create a TSS. So I'm going to split this up here a little bit. I have my GDT stuff, GDT, and then I'm also going to have my TSS stuff. We'll probably start up here. Task state segment. I need a few things for my task state segment. So first of all, I need to have a stack. I'm going to make a stack that is itself a static mute, and it is going to be of some size. And when I realize it's going to be of some size, then I realize I should have a constant that determines what size it is. So I'm going to have a const static size. It's going to be of type usize, because it has to be, because it's the size of a memory object. For whatever reason, BlogOS makes this 4096 times 5. Sure. So we'll do 4096 times 5. Do I have an opinion on how big your backup stack should be? Smaller than your memory. I don't know. To me, that looks like it's chewing up a lot of bits, but like maybe you need those bits, right? Okay, and then I'm going to have a static mute TSS. And that's gonna be this huge thing, right? So we're gonna take the name of the structure, and I think this is relatively understandable. We're looking at the x86-64 crate. We want a data structure of some type. This is the task state segment, and it's called a task state, so that's not too bad. Copy that. Okay. I don't know how to copy paste things. Okay, so I'm going to have something of that type, and it's going to be equal to a new. I'm just going to make a new one. Okay. I've initialized this as a static mute, and I'm gonna fill it with stuff later. Okay, and then I'm also going to make my static mute stack. This one's not going to be too complicated. I'm going to take some U8s of stack size, and then I'm gonna zero initialize them. You probably were exposed to a lot of zero initialization discourse in. You zero initialized in malloc and showed your example code, right?
I think so.
Yeah. So zero initializing static mutes, great way to go about doing things. Right? So that's we've probably seen that before. Okay. We now have all of our static mutes, but we have to set them up. How are we going to do that? Well, we have to somehow take this stack and put it inside the task state segment. And the way I'm going to do this is with some pretty weird stuff. This was like 4 lines of code in blog. You can go look at blog if you want to. But I'm gonna say what I'm doing while I'm doing it. So I'm gonna take my task state segment, which is a static mute. Why did I use a static mute? To me, static mute feels like an idiomatic way to refer to things that persist in hardware that could be modified. So to me, it makes a lot of sense to use this. I am not surprised you're told not to use them in Rust generally. You should not use them in Rust generally. I'm using them here because they correspond to actual existing physical hardware, and I never usually write code that does that because the operating system does that. So this is like almost an operating system almost solution to a real problem. The TSS within it contains an interrupt stack table. We recall this, it contained a PST and an IST. So we've got our things. We're going to index into that at the double fault IST index. That is a really long name. I don't really want to type all of that. I'm going to have to type it a few times, but whatever. I'm going to create a public constant, double fault IST index, and I'm pretty sure it's 0. Here's something I will say I really don't like, and you can't do anything about this. We are indexing with a U16. You should always be indexing with a U size. Why are we not doing that? This isn't like a conventional index. This is an OS level data structure, so it's expecting a 16-bit internal address. Okay. Then why am I casting it as a U size? I don't know what's going on here. I don't understand this. To me, this should be a U size.
Yeah.
And then there should be no cast here. That's what I think should happen. Okay, so then we have equal, and then I'm going to keep writing on one line. x86-64. What are we going to do here? We need a virtual address, but really we just need a way to refer to the stack. And it so happens that the way to refer to that stack is we're going to go through the crate. We're going to ask for a virtual address. We're going to get the virtual address from the pointer. We're going to get the pointer by turning the stack into a pointer in beginning. We're going to capitalize stack because it's a static mute. And then what are we going to do? We're also going to add stack size to this. Why is that? Our stack is going to grow down. So we're going to start at the maximum address we can use in our stack, and then we're going to decrease until we hit the stack location itself. And then there's going to be a guard page there. Okay. Who's going to set up the guard page? Some combination of the crate and the bootloader. We're not going to do that. Okay. I think this code is going to work. What did I press? Weren't we doing a test? How does Rust work? Source GDT.
It's because you didn't do the GDT. The GDT's up there and it's...
Oh, that's crazy. Yeah. No, that makes a lot of sense. I don't know what I was thinking there. Okay, that's fine. Wait, what did we do here?
You forgot an ending brace.
And I think what we actually want to be testing is double, right? Cool. How many tests do we have? Does overflow work yet? This is the one we're trying to do, right? Oh, by golly, we still haven't solved the actual problem. That's so frustrating. I guess we're doing this instead of watching that movie on Wednesday. Why did I say we were watching a movie and then we're going to deal with double fault handlers? That's like one of the worst.
Can you just make this go on your own without any help?
Yeah. Do you want to do it on your own without any help?
I'll probably just do it later today.
Students, confer amongst yourselves and tell me when we get back next time if you want to watch Ghost or if you want me to like help you. Which whenever I help you with the labs, I sit up here and then you all say, Jimmy, constantly, and I just listen to you saying Jimmy for 90 minutes. So decide amongst yourself if you want to do that and come back with your vote on Wednesday.